For real numbers or variable expressions that contain rational exponents, keep in mind a rational number is a fraction, so we'll have some whole number divided by some whole number. What's neat here is that the numerator of our rational exponent will represent the number of factors, and the denominator of our rational exponent will represent the index of our radical sign. What do we mean by that? Well, rational exponents represent radical expressions. So here we're dealing with radical expressions in chapter 9. Note here that for radical expressions at any time, we can write a radical expression using a square root symbol or a cube root symbol, and in general, any radical symbol with index n. If we choose or wish to write any number, variable, or variable expression without the radical symbol, we would use rational exponents. And typically we will use rational exponents for our expressions more often than we will radical expressions. Typically we use the radical expressions to evaluate whatever expression or number, but to express it in terms with variables, we write it with rational exponents. And that's the key here. Normally we want to show off or express our values that are variables or variable expressions. We want to express them using rational exponents. But if we have some real number that has a rational exponent, well, then we can evaluate that. And the easiest way to evaluate it is to view it in terms of a radical value, thus allowing us to simplify down our expression. So here let a be a real number and let n be an integer such that n is greater than or equal to 2. If the principal or positive nth root of a in terms of positive radicands, or if it's a negative radicand, it's a negative principal root. If the principal nth root of a exists, then a with rational exponent 1 over n is defined to be the nth root of a. So note here, for any radical expression for the nth root of a, whether this is the nth root of 5, so let's say it's the cubic root of 5, well, we can rewrite this as 5 to the 1/3 power. For the square root of 4, we can write this as 4 to the 1/2 power. However, if m is some positive integer with no common factor within, then a with rational exponent m over n can be expressed in two ways. A with rational exponent m over n can be expressed as the nth root of a, all raised to the power of m, where a is the radicand under our radical, or our a with exponent m over n can be expressed as the nth root of a to the m power, where our radicand here is a with exponent m. Notice the similarities, notice the differences of two of these equalities here. This is our definition for rational exponents. For our rational exponent 1 over n, the numerator is 1, the denominator is n. Note that for a numerator of 1, that means we have one and only one factor of a. Our exponent that we will work with here, when our numerator is 1, the exponent we will work with is 1. That's why you see there the nth root of a, there is no exponent because it's understood that a is to the first power. So the numerator expresses the exponent in our radical expression. The denominator of n expresses the index of our radical sign for the radical expression. A denominator of n indicates the nth root. For a with rational exponent m over n, where m is the numerator, thus m is going to be the exponent in our expression. N is the denominator, thus n is going to be the index. It will be the nth root in our expression. For both expressions, we have the nth root of some number. For both expressions, we have a power of m. For the first expression, the power of m is attached to the base, that is the nth root of a. For the second expression, the power of m is attached to the base of a, and this a to the exponent m is underneath the nth root power. Which of these would you want to use in either occasion or in any occasion? It's whichever one is going to be easier to help you simplify. In some cases, you'll choose option A, in some cases, option B. But note that each of these can express some base a with rational exponent m over n. Evaluating part A, here we have a base of 8 with exponent 4/3. because our exponent is a rational exponent, to evaluate this real number 8 with exponent 4/3, we want to think about this in terms of the radical expression. Now, we know that according to our definition of rational exponents, we can rewrite, or we can think about, let's not think about rewriting, but just let's think about it in a different way. We have our base of 8. We have our exponent of 4. We have our radical that is going to be the cubic root. Remember that our exponent says the numerator 4 indicates the exponent. The denominator of 3 will tell us what our radical index is going to be. We have a cubic root radical. We have an exponent of 4. So how do we want to write this? For 8 to the 4/3 power, do we want to view this number as the cubic root of 8 to the 4th power? Or do we want to view this as raising to the 4th power some number, the cubic root of 8? Which one of these two would be easier to identify, to work with, without even going to a calculator? No calculator in hand at all. How can we simplify this out? What do we know about that number 8? 8 is not a perfect square. However, 8 is a perfect cube. Notice here our denominator of 3 indicates we're taking the cubic root of something. Do we want to take the cubic root of 8 to the 4th power? Or do we want to take the cubic root of 8 and then take that result and raise it to the 4th power? Well, let's work over here, because what do we know? 8 to the 4th power, I would have to go to my calculator. I do not know what 8 times 8 times 8 times 8 is off the top of my head. Can't do it. Need a calculator. However, for the cubic root of 8, we know this because we know that the cube root of 8 indicates what number do you raise to the 3rd power and to get 8? It's 2. 2 to the 3rd power is 8, thus the cubic root of 8 is 2. So what do we do here? We're going to take not the cubic root of 8, but we're going to take 2 and raise it to the 4th power. 2 times 2 times 2 times 2. Well, 2 times 2 is 4, times 2 is 8, times 2 is 16. In other words, when you multiply by 2, you double. You have 2, double it to get 4, double it to get 8, double it to get 16. 2 to the 4th power is 16. Thus, what is 8 to the 4/3 power? It's 16. Isn't that interesting? When we think, how do you go from 8 to 16? Just multiply 8 by 2, right? 8 times 2 is 16. Well, it's also interesting to note that 8 with an exponent of 4/3 will also result in 16. Well, how is that the case? It's because if you take the cubic root of 8 to get 2 and then raise it to the 4th power, you will get 16. It's also interesting, worth noting that 8 to the 4th power, whatever that result is, 8 to the 4th power is going to be a perfect cube. Why do we know that? It's because the cubic root of 8 to the 4th power somehow results in 16. So whatever 8 to the 4th power, whatever this number is, it is a perfect 4th power because 8 to the 4th is this value, but it's also going to be 16 cubed. Let's try that out in Desmos and just see how these numbers work. It's just multiplication. All these numbers are they're just factors built into these numbers. 8, 2 times 2 times 2, 16, 2 times 2 times 2 times 2. So note here, 8 to the power of 4 over 3 does in fact give us 16. It's also interesting to see here that 8 to the power of 4 gives us 4,096. What happens if we take the cubic root, or the cube root, I should say, of 4,096? Well, of course, it gives us 16, as we would expect. 8 to the power of 4/3 is 16. The cubic root of 8 is 2. 2 to the 4th is 16. We also can see here that 8 to the 4th is 4,096. The cubic root of 4,096 is 16. That's because 8 to the 4/3 is 16. That's also because 16 to the power of 3 is 4,096. Thus, the cube root of 4,096 is in fact equal to 16. Part B, we have 4 squared raised to the 3/2 power. If you think back to chapter 5, section 1, we actually have a rule for this. Recall our power to a power rule that states if we have some base a with exponent m raised to the n power, then we can simply multiply the exponents together. 2 multiply 3/2 is 2 multiply 1.5, which is 3. We also see here 2 multiply 3/2, the 2's cancel, leaving us with 3. 4 cubed, 3 factors of 4, 64. So just by using our power to a power rule in section 1 of chapter 5, well, in that chapter we dealt with only integer exponents. It's worth noting that that rule works for any exponents, any real numbered exponents. Power to a power, multiply together, evaluate 4 cubed to get 64. Another way to view this is, well, 4 squared, of course, is 16, so in parentheses we have 16. So here, what is our actual base when simplified down? What number actually has the 3/2 power? Well, it's 16 that has the 3/2 power. Using our definition of the rational exponent, we can think of this in two ways. Numerator is 3, thus our exponent is 3. Denominator is 2, thus our index is 2. So we're dealing with the square root. So we could rewrite 16 to the 3/2 power as the square root of 16 cubed. We also can write it as the square root of 16 raised to the 3rd power. Now, which one would we want to consider doing? Well, off the top of my head, I know that 16 times 16 is 256, but I do not know what 16 cubed is. I do not know what 256 multiplies 16 is. That would be very difficult. We would need to run to a calculator. The idea here of using this is, for these numbers, can we find the relationship that allows us to simplify without a calculator? Here with this number of 16, exponent of 3 and radical of 2, square root, right? If it's not written, it's understood that exponent is in fact a 2, so this is the square root of 16. 16 is a perfect square. Square root of 16 is 4. Thus here, what number is raised to the power of 3? 4 is raised to the power of 3. Thus, when using rational exponent definitions, 16 to the 3/2 is the square root of 16 quantity cubed, which is 4 cubed, which is in fact equal to 64, either using our power to a power rule from chapter 5, section 1, or using our rational exponents rule in chapter 9, section 1, we can get a simplified resulting value that 4 squared raised to the 3/2 power simplifies down to a result of 64. For 25 to the negative 3/2 power, we do see that our fraction is our exponent is a fraction. Moreover, we see that our exponent is a negative fraction. Recall section 1, chapter 5, the rules for negative exponent. This is our reciprocal rule. What does it mean here? We are not actually multiplying. Our exponents indicate factors. Negative exponents indicate some sort of division. So we have to introduce the division bar. We have to introduce our expression as a fraction. So 25 to the negative 3/2 power, using our negative exponent rule, our reciprocal rule, we can express 25 to the negative 3/2 power as 1 divided by 25 to the 3/2 power. This is how we rewrite our negative exponent as positive. We use our reciprocal rule here. Number 25, what is the reciprocal of 25? It's 1 over 25. Thus, 1 over 25 to the 3/2 power. So what does this mean here? It just means we're going to look to only simplify our denominator. Our numerator is 1, and it's going to stay that way. So now we just work to simplify down our denominator using our definition of the rational exponent. Let's go off and make a sidebar here, and let's look to simplify 25 to the 3/2 power, thus simplifying down our denominator. For 3/2 as our exponent, this indicates a numerator of 3, so we have an exponent of 3, a denominator of 2, thus our radical notation is going to involve the square root radical. Notice for each of these expressions for the definition of the rational exponent, for each of these, the denominator is going to show us what our radical is. It's the square root radical. And our numerator of 3 is going to show us what our exponent is for each of the expressions. Each of these look different, but they represent the same value. And whatever that value is the value of 25 to the 3/2. Which one looks easier to simplify without a calculator, though? Well, 25 cubed, 25 squared is 625. Now, I don't know what 625 times 25 is. If you do, and you know what the square root of that value is, that's very impressive. Let's take a look over here. In parentheses, the square root of 25. What is our square root of 25? What number, when you square it, gives you 25? 5. So square root of 25 is 5. So what actually is our base value here? What number has the exponent 3? 5 has exponent 3. And 5 cubed, 5 times 5 times 5, 125. Thus, 25 to the 3/2 power is equal to 125. But what does that mean for our overall expression? We don't have 25 to the 3 halves power. We have 25 to the negative 3 halves power. Thus, if 25 to the 3 halves is 125, this means that 25 to the negative 3 halves is not negative 125, it is 1 over 125. What we're going to see in future sections, courses, is that when you deal with exponents, our exponent rule says an exponent can be any number. It can be a negative number, it can be a positive number, it can be 0. But the output that you get here, raising some positive number 25 to any exponent, will always result in some positive value. Although our exponent is negative, we might think our output will be negative. Whatever this results in is going to be some negative value, but that's actually not the case. When you have an exponent that's positive, normally you're going to get some bigger value. When you have an exponent that's negative, typically it means you're going to get a smaller value. And in this case here, 1 divided by 125 is going to be a very small number between 0 and 1, closer to 0 than it is closer to 1. So 25 to the negative 3 halves power is 1 over 25 to the 3 halves, which is 1 over 125. As we see on part D, we have some fraction, 64 1/25ths, with a rational exponent, 2/3. We're being told to evaluate the expression. So for part D, think of it this way. We have some fraction raised to some exponent. According to our rules in section 1 of chapter 5, and we want to go back and review chapter 5, section 1, and look at those basic properties at the end of chapter 5 that show all the examples, you will see that when you have a fraction with an exponent, what we'll do here is we'll take the numerator and raise it to the power of the exponent. Likewise, we'll take the denominator and raise it to the power of the exponent. Writing the numerator 64 with exponent 2/3, writing the denominator 125 with exponent 2/3, going to the full view. Now we see here that we can evaluate our numerator separately. We can evaluate the denominator separately. Looking at the numerator 64 to the 2/3 power, coming down to the bottom, how do we want to rewrite this? Using the 2/3 exponent, where 2 is the exponent and 3 is the index for the radical expression, 64 to the 2/3 can be rewritten using the definition of rational exponents, cubic root of 64 squared, or the cubic root of 64 quantity squared. Notice the difference in similarities, and that the similarities are the numerator 2 represents the exponent of our radical expression. The denominator of 3 represents the index of the radical expression. So which one of these two would be easier to simplify without a calculator? Well, 64 squared, mentally, do not know that off the top of my head. However, the cubic root of 64, is there a number such that when you cube this number, you get 64? That answer is yes. 4 to the power of 3 is 64. Therefore, the cubic root of 64 is 4. So what number are we actually squaring? We're squaring the cubic root of 64, which is actually squaring 4. 4 squared is 16. Thus, our numerator, 64 to the 2/3 power, will be numerator 16. Now, what about our 125 to the 2/3 power? Well, we'll do the same thing here. Where again, the numerator of 2 is the exponent, the denominator of 3 is the index for the radical expression. 125 squared off the top of the head, it's very difficult to have to memorize. The cubic root of 125, however, is very easy for us. 125 is a perfect cube. It's the result of cubing 5. Therefore, the cubic root of 125 is 5, and thus 5 squared is 25. Our numerator, rewritten as 16, denominator rewritten as 25. Therefore, 64 over 125 to the 2/3 power can be rewritten as the fraction 16 over 25. And the number 16 over 25 is interesting. What happened here? We cubed something, then we squared something. We squared a 4 to get 16. We squared a 5 to get 25. So just some more things to note here. 16/25ths. This is a very nice, interesting fraction because this is a fraction whose numerator and denominator are perfect squares. Thus, the fraction 16/25ths is also a perfect square. If you take the square root of this fraction, you get the fraction 4/5. That's because the square root of 16 is 4, the square root of 25 is 5, giving you 4/5 as the square root of 16 over 25. But of course, that's not our problem. It just gives us an idea of where this could lead us. The fraction 64 over 125 to the 2/3 power, rewriting that fraction where the numerator and denominator share the common power, simplifying the numerator, simplifying the denominator. Our fraction here cannot be further simplified, thus we are done. We have evaluated this rational exponent using our rules of radical expressions, 16/25. We want to look at parts E and F together because notice E and F look very similar. E here we have the negative of 16 to the 1/2 power. Part F, however, we have the quantity negative 16 to the 1/2 power. Notice the similarities and difference for E and F. For F, what is our base? Well, for part F, notice in parentheses the negative 16 is all being raised to the 1/2 power. Thus, our base for part F is negative 16. However, for part E, our base is positive 16, although there is a negative out in front. Notice here the negative is attached to the 16 because of the parentheses involved. No parentheses here indicate we have the negative of something. So for this negative 16 to the 1/2 power, the 1/2 power is attached only to our base of 16. Here the 1/2 power is attached to the negative 16. So let's take a look here at parts E and F. For 16 to the 1/2 power, how do we rewrite this? Well, leaving that negative out front, and now the 16 to the 1/2 we express in our radical form. Well, here the 1/2, the numerator 1, that's our exponent of 1. Denominator of 2, that is our index for the radical expression. Here we have the second root of 16 to the first power. Well, 16 to the first power is simply 16. And of course, any index of 2 is understood to be the square root, and you do not have to write it. That's only for n equals 2, of course. We have here the negative of the square root of 16. In other words, what is our negative root? What is our negative root for 16 here, our negative square root for 16? Well, square root of 16 is 4, thus we get negative 4. Keep in mind here that for 1 over n, if our numerator is 1, we're looking at the square root, the cubic root, the fourth root, and the exponent is not needed because the exponent's 1. The 1/2 power is the square root. We're taking the square root of 16 and we're attaching this negative out front. The negative of 16 to the 1/2 is the negative square root of 16, which is negative 4. Now, what about here? Similarities and differences. What we're saying here is that our base negative 16 has exponent 1/2. Thus, we are taking the square root of negative 16. To evaluate the square root of negative 16, we see here that we have as a radicand negative 16, that is a negative number under the square root sign. Remember that the square root, the fourth root, and in general, any index that is even cannot contain a negative radicand. There is no number such that when you square that number, it will result in a negative 16. Only positive values are 0. Thus here, the square root of negative 16, as we will see in section 6, will be defined as an imaginary number. For now, we will say this is a non-real number. It is a non-real number because it is an imaginary number. Taking the square root of a negative number, like we see for part F, is defined to be an imaginary unit. In the following exercises, 81, 83, and 85, evaluate without using a calculator. For number 81, we have the fraction 8/27 raised to the 2/3 power. As with any fraction raised to a power, we will assign the numerator the power of 2/3 and assign the denominator the power of 2/3. This is our rule for fractions with exponents. According to chapter 5, section 1, any fraction raised to an exponent is equivalent to the numerator raised to that exponent divided by the denominator raised to that exponent. We will look at each numerator and denominator as a separate problem. 8 to the 2/3 power, we have seen this previously in our videos. 8 to the 2/3 can be expressed as the cubic root of 8 squared, or could be expressed as squaring the cubic root of 8. Now, which one we want to do here? 8 squared is 64, and the cubic root of 64 is 4. Similarly here, the cubic root of 8 is 2. 2 squared is 4. Therefore, 8 to the 2/3 power, as we see using our definition of the rational exponent, 8 to the 2/3 is 4. Want to see that relationship that when we have a rational exponent where the numerator is smaller than our denominator, 2 is smaller than 3, therefore our rational exponent will indicate for the base of 8, our result will always be a number that's smaller. When your exponent is a number that is less than 1, in other words, the numerator is smaller than the denominator, the output here will always be a number that's smaller than your original base. We started with an 8. The 2/3 power for 8 is 4. In other words, cubic root of 8 squared, 2 squared is 4. What about 27 to the 2/3 power? The 2/3 power indicate we should get a number smaller than 27, and what would that be? Well, 27 squared is a large number, say 729, something like that, and the cubic root of 729 is 9. And let's see how we can do that. Instead of looking at 27 squared, let's look at the cubic root of 27, which is 3. Thus, 3 squared is 9. So what do we get here? We get that the fraction 8/27 raised to the 2/3 power actually equals 4/9. Using our rational exponent rules for section 1. The next one we'll take a look at here, number 83. We have the fraction here 121 over 9 raised to the negative 1/2 power. First thing we notice here is our exponent is a fraction 1/2, but it's a negative 1/2. What do we do with our negative exponents again? Remember that the negative exponent rule is also referred to as the reciprocal rule. What does a negative exponent indicate? It indicates the reciprocal value. Here, 121 over 9, what is the reciprocal of our fraction 121 over 9? Switching the numerator and denominator for number 83. By switching the numerator and denominator, writing this fraction as the reciprocal, 9 over 121. By switching the numerator and denominator, we now can make our exponent positive. So as we see, 121 over 9 to the negative 1/2 power is equivalent or exactly equal to 9 over 21 to the positive 1/2 power. Again, what do we see here? A fraction raised to an exponent. Take the numerator 9, raise it to the 1/2 power. Take the denominator of 121, raise it to the 1/2 power. What does it mean here? For a rational exponent of 1/2, we'll recall that the 1/2 power represents the square root, radical notation. So the 1/2 exponent directly corresponds to the square root sign. 9 to the 1/2 is the square root of 9. 121 to the 1/2 is the square root of 121. That works out nicely for us here because 9 and 121 are both perfect squares, and that when you take 3 and square it, you get 9. When you take 11 and square it, you get 121. Thus, the square root of 9 is 3. The square root of 121 is 11. So what do we get here? Our original expression that we begin, with which we begin, is equivalent to 3 over 11. 3 over 11 is a fraction that's simplified according to chapter 7. This numerator and denominator do not share common factors. Why is that the case? Well, 3 and 11 are actually both prime numbers. So they only share the common factor of 1, which does not help us simplify. Therefore, 3/11 is fully simplified, and it is our simplified expression for number 83. Now, number 85 here, we have in parentheses negative 3 raised to the 3rd power, and that is raised to the 2/3 power. Now, we've seen something similar to this before. And that in chapter 5, section 1, our power to a power rule indicates that if we have any base with an exponent raised to an exponent, multiply these two exponents together and get one single exponent. 3 multiply 2/3. If you have 2/3 3 times, you have 2/3, 4/3, 6/3. In other words, 3 times 2/3 is 6/3. But what is the fraction 6/3? As a rational fraction, yes, it's 6/3. It reduces down to 2/1, which is just 2. 6 divided by 3 is 2. Again, what does it happen here? We're working with the exponent. This -3, best expressed in parentheses, because we multiplied the exponents together. And what is our base? Our base is the -3 in parentheses. -3 is going to be squared. And squaring a -3 here is going to give us +9. Another way we could see this, going to the full view. What happens if we go ahead and evaluate what is in parentheses? Well, as you see in parentheses, we have an exponent of 3 attached to this 3. Now, the parentheses here indicate this exponent. This 3 here has exponent 3. This negative is not assigned with this exponent of 3. What is the base for the exponent of 3? It's the 3. However, what is the base for the exponent 2/3? It's -3 cubed. So by looking at 3 cubed, 3 to the power of 3 is 27, but we have the negative out front. In parentheses, we have -27. Now, to the 2/3 power here, we can either square -27 and then take the cubic root, or we can take the cubic root of -27 and then square it. Let's try that here, because as we see, 27 is a perfect cube. Likewise, -27 is a perfect cube. The denominator of 3 in our exponent indicate the index of our radical. The numerator of the exponent indicates the exponent for our radical. The cube root of -27 is -3. And thus, when we square the cubic root of -27, we're squaring -3. -3 multiplied -3 is going to give us 9. So for number, I do not believe it's 83 at this point. We have moved on. We're looking at number 85. Number 85 here, -3 raised to the 3rd power, all raised to the 2/3 power. Either using our power to a power rule to simplify and evaluate, or by using our simplification, evaluating on our own here, and then using our definition of the rational exponent here. Power to a power got rid of the rational exponent, allowing us to evaluate. Evaluating, rational exponent definition, simplifying to get the -3 squared to give us +9 as our simplified value. In the following exercises, 89 through 99, rewrite the expression using rational exponents. For number 89, we have the square root of t. Keep in mind that the square root of t here, the index is understood to be 2. T is understood to be to the 1st power. The square root of any number to the 1/2 power. Thus, we have t to the 1/2 power. Here for number 91, we have x multiply the cube root of x to the 6th power. I do want to express there that the x is sitting next to the radical expression, thus it is indicating multiplication. X is multiplying the cube root of x to the 6th power. Now, using the rational exponents, the cube root of x to the 6th power can be rewritten using rational exponents, x to the 6/3 power. So we have here x multiply x to the 6/3 power. Now, our rules of integer exponents state that if we multiply like bases, multiplying these bases of x here, we can add the exponents. With an understood 1 and a 6/3, which simplifies down to give us 2, Six-thirds simplifies down to an exponent of 2. 1 plus 2 gives us the exponent of 3. So we have here for number 91, x cubed. The product of x and the cubic root of x to the 6th power, which is simply x multiply x squared. X multiply x squared is x cubed for 91. Here for number 93, we have u squared. And this is going to multiply the cubic root of u. But how can we write the cubic root of u? Very similar to the square root of t. Very similar to the cubic root of x to the 6th power. The cubic root of u, where u is understood to the 1st power, that is u to the 1/3 power. So now as we see, when we multiply these bases of u, we add the exponents 2 and 1/3. Now this would be correct, right? If we add these exponents 2 and 1/3, we can write it as 2 and 1/3. But notice here that as it's a mixed number, adding a 2 and a 1/3, 2 and 1/3, how can you write this mixed number as an improper fraction? In other words, how can I write this not as a whole number and a fraction rather just one fraction? Well, what we're going to do here is we're going to convert 2 into fractions of 3. All we have to do that is 2 times 3, which is 6, plus 1, which is 7. So 2 and a third is 7/3. U to the 7/3 power. Again, how do you do that? 2 and a third? Well, how many thirds is 2? It's 6/3, as we see up here, right? 6/3 equals 2. This is another way to rewrite 2 as a fraction with denominator 3. Let's do that down here. If I rewrite 2 as 6/3, the fraction 6/3 is 2, but it allows me to add 2 to a fraction 1/3. Here, 2 plus 1/3 is 2 and a third, which is combining the numerators because we have a common denominator now, 6 plus 1 to give us 7/3. U to the 7/3 power. For number 95, we have a quotient. We have a division. For number 95, we have here the square root of x divided by the square root of x cubed. Now for number 95, to perform this division here, we want to rewrite using rational exponents, because then, according to section 1 of chapter 5, we can use our rules of exponents to subtract. The quotient rule indicates that if we are going to divide like bases here, we're going to divide x by x for number 95. Therefore, in order to divide, we subtract the exponents. But what are the exponents? For the square root of x, similar to the square root of t, the square root of x is x to the 1/2 power. We are dividing x to the 1/2 power by the square root of x cubed. The index of the square root is 2. X cubed has an exponent of 3. We write this as the rational exponent, 3 over 2. For number 95, our denominator is x to the 3/2 power. Now we are dividing x's. We have an x divided by x, but it's x to the 1/2 power divided by x to the 3/2 power. Section 1 of chapter 5 says when we divide by like bases, we subtract the exponents. 1/2 subtract 3/2. If we're dividing by this, we're getting rid of. You divide something out, making it smaller, getting it smaller. Subtract 3/2. Now, because we are subtracting fractions with a common denominator, we combine the numerators. 1 minus 3. This is going to give us the exponent negative 2/2, which of course 2 over 2 is 1. This is the exponent negative 1. X to the negative 1 power. Now it says here, you rewrite the expression using rational exponents. The exponent here, negative 1, is a rational exponent. A rational number is that of a fraction. Negative 1 is understood to be a fraction. It can be written as negative 1 over 1. Therefore, it is a rational number. It is a rational exponent. But remember that with any negative exponent, we can always make it positive. To make any negative exponent positive, simply take the reciprocal of your base. Our base here is x. Once again, x is understood to be x over 1. If we write it as a fraction, the reciprocal of x over 1 is 1 over x. So x to the negative 1 power becomes 1 over x to the first power, which is simply just 1 over x. Now, what about numbers 97 and 99? Give you a moment to write those down. And see that for number 97, this is a quotient. Therefore, we will subtract the rational exponents. For the 4th power of t, this is t to the 1/4 power. For the square root of t to the 5th power, this is t to the 5/2 power. For number 99, the cubic root of x squared can be rewritten as x to the 2/3 power. We have there the cubic root of x to the 7th power, which can be rewritten as x to the 7/3 power. Now, x to the 2/3 multiply x to the 7/3. When you multiply bases, you add the exponents. 2/3 plus 7/3 is 9/3. 9 divided by 3, of course, is 3. Thus, for number 99, we simplify down to x cubed. But what about 97 there? Number 97. Give you a moment to write t to the 1/4 power, subtract t to the 5/2 power. Find that the fractions 1/4 and 5/2 do not share a common denominator, thus we must find a common denominator. Looking at 97. With 97 here, t to the 1/4 power divided by t to the 5/2. And we used our rational exponent definition to rewrite the numerator and denominator, and now using our quotient rule from section 1 of chapter 5, subtracting the exponents, because we are dividing like bases, we're t divided by t. We subtract the exponents, 1/4 minus 5/2, but those denominators are not the same, therefore we cannot combine these fractions. We must find a common denominator using the 4 and the 2. What is the LCD of 4 and 2? In other words, what is the smallest number such that 4 and 2 will both divide into? That's 4. Leaving 1/4 as 1/4, rewriting 5 over 2 as a fraction with 4 as the denominator, multiplying the top and bottom by a 2, we get the fraction 10/4. So 1/4 minus 5/2 is actually 1/4 minus 10/4. And because our denominators are now the same, we combine the numerators, 1 minus 10, which is negative 9. T to the negative 9/4 power. Now it says, of course, here to rewrite using rational exponents. There is our exponent. We have t expressed one time. T has the exponent negative 9 over 4. To make it positive, place it in the denominator. 1 over t to the 9/4 power. Give you a moment here to pause the screen and write down the summary of rules of exponents. This is from chapter 5, section 1. We have our rules, our product and quotient rules that we've been working with, properties 1 and 2. Our power rules there, most notably number 4, our power to a power rule that we worked with quite often. We will also use these properties in these rules of exponents as we move forward in chapter 9, because with chapter 9 we are going to deal with simplifying radical expressions, and some of these simplifications will deal with us having to rewrite using rational exponents. So if we can rewrite our our radical expressions, those involving the square root, cubic root, etc., if we can rewrite these radical expressions using rational exponents, then we can use these rules of exponents to simplify our radical expressions. Of course, any number to the 0 power is 1, and our reciprocal rule for number 7 and 8 state that any base with a negative exponent can be rewritten as 1 divided by the base to the positive exponent. Number 8 says any fraction with a negative exponent rewrite as the reciprocal to the positive exponent. A radical function is a function that contains a radical, such as the function f of x equals the square root of x, or the function g of x equals the cubic root of x. When evaluating a radical function, note that the radical symbol is a symbol of grouping. To describe the domains of the following functions, f of x equals the cubic root of x, and f of x equals the square root of x cubed, let's consider our rules below. It says let n be an integer that is greater than or equal to 2. If n is an odd integer greater than or equal to 2, then the domain of the following function, nth root of x, is the set of all real numbers. In other words, for any radical function that has an odd index n, the domain can be any real number from negative infinity to positive infinity. In other words, you can plug any number you want into a radical function whose index is odd. However, if the index is even, property 2 here, if n is even, the domain of the following function, nth root of x, is the set of all non-negative real numbers. What does that mean there? All numbers that are positive or 0 are non-negative. You're not negative, you're positive or 0. In other words, remember that you cannot take the square root of a negative number, nor can you take the 4th root of a negative number, the 6th root, or any even root power. The number that is our radicand here cannot be negative. Therefore, our radicand for an even index radical function, the radicand cannot be negative. It must be 0 or positive. In other words, non-negative. If n is odd, if our index is odd, cubic root, fifth root, seventh root, etc., the radicand can be any value, negative, 0, or positive. So looking at the domains above, for the cubic root of x, because our index is 3, that is an odd number. The domain for f of x equals the cubic root of x will be every single number from negative infinity to positive infinity, expressed in interval notation as such. The domain of any radical function where the degree or the index n is odd, the domain is every number from negative infinity to 0, or negative infinity to positive infinity. However, if n is even, such as f of x equals the square root of x, or the square root of x cubed, whatever the case may be, what numbers can you plug in to that function there? Well, if n is even for the square root, fourth root, sixth root, etc., then the radicand can only be a number that is 0 or positive. In other words, any number from 0 to infinity. So this represents the non-negative real numbers. In other words, these are the numbers, I want to include 0, so I don't want to use parentheses, right? Remember that when we work with interval notation, if we want to include an endpoint, we use a bracket, not parentheses. Here, 0 is included because the square root of 0 is in fact 0. That gives you out a value. Recall that the domain is the set of numbers that give you an output value. If I plug in a negative number to the square root of x, it does not give me out a real number. Therefore, I can't plug in a negative number, therefore it's not in the domain. Recall that rule for the domain of a rational function. The domain of a radical function simply says if our index is even, the domain or our radicand has to be greater than or equal to 0. Remember that this interval expresses numbers that are greater than or equal to 0. However, if we are working with a function that is radical, whose index is odd, choose any real number in existence, either negative, positive, or 0, and you can plug it in to that function. Therefore, the domain above for part A is all real numbers from negative to positive infinity. For part B, it's only those numbers from 0 to positive infinity. To evaluate the radical function when x equals 4, simply substitute 4 anywhere you see the variable x. For part A, to evaluate the function when x is 4, we simply state that f evaluated of 4, f of 4, for when we have the function cubic root of x minus 31, we have here the cubic root of 4 minus 31. And what do we have for 4 minus 31? Well, 31 minus 4 is 27. Therefore, 4 minus 31 is negative 27. And what do we know about here? The cube root of negative 27. What number do you raise to the third power to get negative 27? It's negative 3. So our function evaluated at x equals 4, function equals negative 3. And what you would see is if you were to graph this radical function, the ordered pair x equals 4, y equals negative 3 would be an ordered pair solution to this function. Thus, it would be on the graph of this radical function. What about part B here, g of x? Well, here for our function g evaluated at 4, if we substitute 4 for the variable x, we have here the square root of 16 minus 3 times 4. Well, to find 16 minus 3 times 4, 3 times 4 is 12. 16 minus 12 is 4. And what do we know about the square root of 4 here? 2. Thus, when we allow x to equal 4 and we plug it into this function here, the function spits out the value of 2. When x is 4, the function equals 2. Thus, the ordered pair x equal to 4, y equal to 2, that ordered pair would lie on the graph of this function here, this radical function, square root of 16 minus 3x. And here, that function, when x is 4, the function equals 2. In the following exercises below, number 143, evaluate the function for each indicated x value. For 143, we have the radical function f of x equals the square root of 2 times x plus 9. Here we are being told to evaluate for parts a through d, f evaluated at 0, 8, -6, and 36. To evaluate the function at each of the indicated x values, simply substitute the value of x into the function. For part a, the function evaluated at 0, f of 0, simply take the function and substitute 0 for x. We can just go ahead and do this for each of the values of x. Notice the repetitiveness there, just trying to find the pattern. For the first evaluation, when x is 0, what does the function equal? Well, 2 times 0 is 0. 0 plus 9 is 9. So here we have the square root of 9, which of course is 3. So for our function here, when x is 0, the function is 3. Now what does the function equal when x is 8? 2 times 8 is 16, plus 9 is 25. So the square root of 25 is 5. So our function, when x is 8, the function is 5. What about -6? Well, 2 times -6 is -12. -12 plus 9 is -3. What do we know about the square root of -3? Well, the square root of any negative number is an imaginary number. Therefore, the square root of -3 here is undefined or non-real. When we talk about the domain and range of a function, it's what numbers are being plugged into the function, what values are coming out. Here, we're plugging in a 0 and an 8, and we're getting out a 3 and a 5. Those are all 4 real numbers. In other words, when you plug in a 0, you get out a 3. Therefore, the 0 is in the domain of this function. 3 is in the range. You plug in an 8, you get out a 5. Therefore, the 8 is in the domain of the function. The 5 is in the range of the function. You plug in a -6 to this function, and you do not get out a real number. The square root of -3 is a non-real number. Therefore, -6 is not in the domain of this function. How do you know what values are not in the domain of this function? Well, remember that this is a square root function. The index is 2. That's even. Therefore, our radicand must be either 0 or positive. It just can't be negative. In other words, 2x plus 9 must be greater than or equal to 0. In other words, if it's greater than 0, it's positive. If it's equal to 0, it's 0. What is it not? It's not less than 0. Less than 0 means negative, and you can't take the square root of a negative number. Therefore, what values of x are you allowed to plug into this function? This will define the domain of your function. Solving for x in this inequality to get x by itself. X multiplied 2 plus 9. So let's reverse those steps and subtract 9 and divide by 2. Subtracting 9, we get that 2x is greater than or equal to -9. To get x by itself, divide by 2. X must be greater than or equal to 9 halves. 9 halves is -4.5. So to be greater than -4.5 is -4, -3, -2, -1. Actually, I should be counting up. Here we're at -4.5, -4, -3, -2, -1. You're going up towards 0, and then you get into the positives. What's less than -9 halves? Well, that's -5, -6. Because -6 is less than -9 halves, it would tell us that -6 is not in the domain. What does that mean? It means if you plug -6 into this function, you get a non-real number. If you plug any number less than -9 halves into this function, you will get the square root of a negative, which is defined to be an imaginary value. So it's not in the domain. What is in the domain? Any number that's greater than or equal to -9 halves. That, of course, includes 36. 36 is greater than -9 halves. 8 is greater than, 0 is greater than -9 halves. Thus, when you plug them into the function, you will get an output value that is a real number. Thus, they are in the range of your function. These numbers are in the domain. -6, however, is not. 36 will be, because it is greater than -9 halves. Let's see what number corresponds to 36. 2 times 36 is 72, plus 9 is 81. The square root of 81 So what we see here, you plug in a 36, you get out a 9, indicating that 36 is in the domain of this function. 9 is in the range of the function. To find the domain of the following radical function, f of x equals the square root of 2x minus 1, we first observe that the index is not given to us, so it's understood that the index is 2, and this is a square root function. The square root telling us that the index is 2, meaning that the index is even. This means that our radicand, whatever is under the radical sign, must be greater than or equal to 0. What is our radicand? It's 2x minus 1. So what this means here, the domain of this function, it all depends on that expression 2x minus 1. Well, that expression 2x minus 1 must be greater than or equal to 0. It just can't be less than 0. If it was less than 0, it would be negative, and we can't take the square root of a negative number. So 2x plus 1, or 2x minus 1, if it represents the number 0, then let 2x minus 1 equal 0, and you're good to go. Here, though, we want to know what is the domain. This is the set of x values. We know that you can plug any number greater than or equal to 0 under this expression, but what does that mean for the variable x? What will it be allowed to be? Well, now we just need to solve for x here. In order to get x by itself, x is being multiplied by 2, and we're subtracting 1. So to reverse those steps to get x by itself, adding 1 to each side, we get that 2x is greater than or equal to 1. To get x by itself, divide 2 on each side. As long as you plug in any number greater than or equal to 1/2 into this function, you will get a real number out of it. That's what this means here. What happens if you plug exactly 1/2 into it? Well, this happens every time. You'll always get out a 0. Let's see what happens. Because it says, right, x greater than 1/2 or equal. Well, whatever number you get over here when you isolate x, watch what happens when you plug it back in. 2 times 1/2, what's half of 2? It's 1. 1 minus 1 is 0. The square root of 0 is 0. Now, any number larger than that is going to give you a value larger than 0. Say you plug in 1. 2 times 1 is 2, minus 1 is 1, the square root of 1 is 1. Let's say you plug in, I don't know, 5. If you plug in x equals 5, 5 times 2 is 10, 10 minus 1 is 9, the square root of 9 is 3. So we are increasing. As the x gets bigger, the function gets bigger, because we can compare those y values. What is the domain? It's any number greater than or equal to 1/2. But expressed in interval notation, what are those intervals of numbers? Well, 1/2 is the smallest possible value. We can get larger than 1/2. It can be greater than 1/2. Well, what's large? What's the largest number above 1/2? There is no largest. So we assign that placeholder of positive infinity. It indicates that our numbers can continue to get as large as we want it to be. 1,000, a million, a billion, a quintillion, quadrillion, whatever it is. Continue to get as large as you want, growing towards positive infinity. We always put parentheses around infinity. However, the 1/2 here, it says x can be greater than or equal to 1/2. We want to include 1/2 in the domain, thus we use the bracket notation. And so our domain, the set of usable numbers, the set of input values that you plug into a function such that the output value is a real number, the domain here, all the usable numbers greater than or equal to 1/2.